For section 3.4, we're going to be solving exponential and logarithmic equations. We're going to have to use some properties of logarithms, possibly exponents. We're going to see different types. And this is kind of like a really large section, so let's make sure that we can get through as much as possible here in our lesson. So the first task that we're going to have today is solving exponential equations that have a common base. In Algebra 2, I used to call these the baby base questions. So like right here, for instance, 4 and 16 share a common base. If you could rewrite 16 as a 4, then this would be a really easy question to solve. So keep 4 to the x minus 1 power as it is, but instead of 16, what if we wrote that as 4 squared? Well, 4 squared, that's already being raised to an x power, would become 4 to the 2x power when I utilize my exponent properties. And then the only way for this equation to be true is if your exponents match. So we're going to say x minus 1 equals 2x, and then subtract 1x, excuse me. So negative 1 equals x. And we do want to kind of think about checking our answers. It doesn't happen so much in exponential equations, but in logarithms we often will have extraneous solutions. Oh, it was already done for us. My bad. All right, so this next one. Oh, this is a fun one. So it's actually a quadratic. So what we're going to do is we're going to do a little u substitution. So why don't we let u equal e to the x power. So anytime I see an e to the x power, I'm going to replace it with a u. So like for instance here, this is really u squared, because e to the x power squared is e to the 2x. And then minus 3 times u plus 2. Well, we now have a quadratic. So that's fun. We can factor it. Factors into u minus 2 times u minus 1. And then I solve and I get u equals 2 and u equals 1. But remember, u wasn't the question. The question was, what is x? So instead of u, we're going to rewrite this as e to the x equals 2 and e to the x equals 1. And now we're going to be applying a natural logarithm to both sides, because that would be solving an e. It would cancel out with the base e. So the first solution is natural log of 2, which is some decimal. And then the second solution is natural log of 1, which is, I don't know, I feel like I've already done this question. It's 0. I knew that. All right, so natural log of 2, if you type that in your calculator, I don't have a decimal equivalent to that, but natural log of 1 is just a 0. So that was a really challenging question where we had to recognize, oh geez, there it is again. So we had to recognize that it was already a quadratic, and we could do a little substitution work. That was a very advanced question, so don't panic if that was weird. So we're going to skip this next example for A. It's already done for you, I think, on your sheet. B is also done for you on the sheet. So the first issue is if I'm going to solve for this question, I can't do baby bases, but if I added the 6 over, I would rewrite it as e to the 8x plus 1 equals 7. And now would be a good time to apply a logarithm. And you know when they have answers like around to the nearest hundredth, you're not going to have anything pretty. So the good news is natural logarithm and e will cancel, and you get 8x plus 1. And then natural log of 7 is something. I don't know what it is off the top of my head. But the next thing I'm going to do is I'm going to type natural log of 7 in. Oh, you know what? This is another one of those where I already solved it. So over here, in text, they wrote the solution. Remember, this is the one we skipped. But right here, was where they took natural log of 7, they subtracted 1, and then divided by 8. So if you did that in your calculator, remember, you can just keep using the previous answer as opposed to retyping the decimal in. But they're encouraging you to not type anything in until you're ready to solve. Either way, you end up with approximately 0.12 as an answer. So those last two examples we did, the base E1 here and the base E1 here, we used a natural logarithm because natural logarithms and e's will cancel each other out. But we're back to the baby base question. Those are the two types of three types technically of exponential equations that you're going to see. So if it has a baby base, please try to utilize them because they make your math really easy. If it has to be substituted so you can do some quadratic algebra, so be it. And then if it's just got a base that I can't really do anything with, we're just going to have to apply a logarithm. And remember, your calculator has quick keys for natural log and common log. So those are typically the two types of logarithms that we're going to use to bring down those exponents. So here for number 1, I think I could rewrite 9 as a 3 if I rewrite it as 3 squared. So if you have 3 squared already raised to the x power, this side of the equation is really 3 to the 2x. And then this side of the equation is 3 to the 3x minus 4. So now that they have a common base, the only way for this to be true is with your exponents equaling each other. So 2x equals 3x minus 4. And then we solve. So negative x equals negative 4, which means x equals 4. Oh boy, this one's fun. 1/4 and 1/8, the common base. There's a couple of different common bases we can do. I'm going to just rewrite them as 1/2. So 1/2 squared is 1/4. But remember, it's already to the 2x minus 1 power. And then 1/8 is like 1/2 to the 3rd power, but raised to the 11 minus x power. So using my exponent properties and combining these exponents, I end up with 1/2 to the 4x minus 2 power equals 1/2 to the 33 minus 3x power. And now that I have common bases, I can just equate their exponents together. The only alternative for solving this equation would be to apply logarithms to both sides. And since the 1/2 base is not really that great, you're going to be using a lot of logarithm work on your calculator. And no one really wants to do that because it's not a lot of fun. So believe it or not, this was the easiest way to do the question. We're going to add 3x over. Also going to add this 2 over. So we end up with 7x equals 35 and x equals 5. So it is a little tricky to see who the common base is. Sometimes it's not as simple as just, oh, obviously. So this next one does also have a common base. If you think about it, I could rewrite a couple of different ways. I'm going to keep, let's see, oh, neither one. I'm going to rewrite them both as 2's. So 4 is going to become 2 squared, and then 1/2 is going to become 2 to the negative 1st power. But remember, there's existing exponents already. So when you multiply the existing exponents together, and you multiply them over here as well, you end up with 2 to the 6x minus 4 power equals 2 to the negative 2x power, and then we can go ahead and set those exponents equal to each other. So I actually, whenever I'm taking a test or doing a lot of these questions, I kind of fingers crossed hope that they give me a lot of baby-based questions, because technically they're the easiest kind, in my opinion, especially if you don't have a calculator and you have to keep weird answers. Dyslexia, don't hit me now. I got to divide by -8, and I end up with a 1/2 for a solution. There we go. 0.5, of course, is the same thing. All right, the next one is a glob of fun. So the solutions are not pretty, and we could tell that by trying to graph it on our calculator. So that tells me that we're probably not going to be able to do any like baby-based question, but I could already tell we couldn't do baby bases because it's base E. Like, yuck, E's gross. So, excuse me, snacking. This is one of those questions where we're going to do that U substitution business. Whenever you notice it looks like a quadratic and the middle term is e to the x power, that is what you're going to replace u with. So e to the x power is now going to become u, which means this is 2 times this is u squared plus 12u. Come on, buddy. And then minus 54 equals 0. So I'm going to solve this quadratic through normal methods. I do notice everything's divisible by 2, so let's take care of that. And I end up with u squared plus 6u minus 27. So factoring this into u, let's see, plus 9u minus 3. And then don't forget, we still have to solve because u isn't even a thing in this question, and we're looking for x. So u could be -9 or 3 until I go back and substitute, because remember, u is e to the x power. So e to the x power equals -9, and e to the x power equals 3. Well, trying to solve this equation, I would apply a natural log to both sides. But if you try to take the natural log of -9 over here, you're going to find out that that solution is not real. You could try typing it in if you'd like. But over here, natural log of 3 is something. You could either leave your answer as natural log of 3, Or, you know what, I never wrote this as a decimal equivalent in my calculator, so whatever natural log of 3 is, that's my only viable solution here. All right. We're going to skip 5 for now. Let's look at number 6. So, not going to end up with a common base since it's a base e, but I am going to try to isolate that base e before I apply a logarithm. So if I divide by 2.4 on both sides, I get e to the x minus 6 power equals 3.875. So then when I choose to apply a natural log, these cancel, and you get x minus 6 equals, I think it's 1.35, roughly. And then if I add 6 to both sides, I get an approximate answer of 7.35. Okay. So this question, it looks like it should have a common base, because 3 and 6, I mean, they have some things in common, but it's not going to be powers and bases that are common. So we do have to just kind of suck it up and apply the logarithms. Now you can choose to use natural log or common log. This sounds really lazy, but I always use natural log because it's one less letter. So if I apply a natural log to both sides of this equation, remember the whole point of a logarithm is that the x will come down, or the exponent will come down in front. So you have a 2x down in front of the natural log of 3 equals, and then this exponent will come down in front. So x minus 1 times the natural log, that's natural log of 6. Again, if you used common log, it's going to look similar, except you're going to have common logs here and here. So from here, you have a couple of choices. 2 times x times natural log of 3. Well, 2 times natural log of 3 is actually, it's not too bad. Ignore the x for a minute, but it's 2.197x. I just multiplied 2 times natural log of 3 on my calculator. And then I'm going to go ahead and I'm going to distribute this natural log of 6 into here. So I get 1.792x minus 1.792. And I know I've already kind of truncated decimals, but I'm okay with that, guys. If you keep enough decimals in your work, or most of you are really good at just keeping the entire answer in your work by using the answer command, rather than truncating it at all, that's okay. So here we get 0.405x equals negative 1.792. And then dividing both sides by 0.405, we get approximately negative 4.42. Okay. Looks like we're skipping 8. Good news. So those were for particular types of exponential equations. So what we're going to look at now are logarithmic equations. And the idea is if a logarithm undoes an exponent, then an exponent would undo a logarithm. So the key word today is we're going to be exponentiating the equation. But first you have to isolate the logarithm. So your first job is to get this logarithm completely by itself. We're going to start by adding the 1 over. I think this is one of those cases where if I switch to the next slide, it's already worked out for me, but oh well. So log base 5 of 4x equals 12. And then we're still trying to isolate, so I'm going to divide by 2. So right now I have log base 5 of 4x equals 6. Now, some algebra teachers teach this where you just use that rewrite formula, base to the answer equals the number, and then you go through and you solve the equation that way. But I would like you to recognize where this is really coming from. The way we get rid of a logarithm in an equation is to create an exponential function. So you can literally do anything to an equation as long as you don't change the balance of it. So what I'm going to do is I'm going to take a base of 5 and I'm going to shove it underneath the problem. So now we have 5 to the log base 5 of 4x power equals 5 to the 6th power. Sounds kind of weird, right? So here, these cancel, and you get 4x equals whatever 5 to the 6th power is, right? And then when we divide by 4 on both sides, it's not pretty. It's a pretty big number, in fact, and I definitely would be using a calculator on this, 3906.25. Lovely. So what we just did here is referred to as exponentiate. So the art of like taking a base, shoving it under a problem, and then having the logarithm and the exponential base cancel each other out. Now, in this screen, the teacher that wrote up this sample, they did that thing where they just rewrite base to the answer equals a number. It ends up being the same thing. I feel like for those of us who just really enjoy equation solving, if we understand that exponentiating is actually a thing we can do to equations, it's going to help you in the future. Okay? The idea here on this question is we have multiple logs going on, and I don't really know if I like the way it looks at the moment. So the first thing we have to do is bring the logarithms together into one equation. So if you don't mind, I'm going to go ahead and add this logarithm over here. So I have a slow tablet. Here we go. Log base 2 of x minus 6, and then it's being added to log base 2 of 2x. Still equals 5 on this side. And now I'm going to use my condensing formulas and bring that together as one logarithm. So log base 2 of, remember we multiply these together, so it's 2x squared minus 12x. That's what happens when I multiply this times this, equals 5. And then again, if I want to undo a logarithm, I could exponentiate with that same base. So I'm going to take a 2, I'm going to shove it under this side of the question, and also over here. So this becomes 2x minus squared minus 12x. 2 to the 5th power is 32. Then I have a lovely quadratic, which I just love solving quadratics, you know. It's a standard form. I do notice there's a common factor of 2, so let's get that 2 out of there. So we end up with x squared minus 6x minus 16. And then solving, let's see, x minus 8 times x plus 2, which gives me a solution of x equals 8 and x equals negative 2. Now these are logarithmic equations, so it would be smart of us to plug these in and make sure they work out. The idea is once you're in a logarithm, whatever is inside here, once you simplify, cannot be negative, because you can't apply a logarithm to a negative value. It would be undefined because it would be imaginary. And that's not going to happen here because of the quadratic algebra. So both of those answers are good. So those are the things worked out. Yay. Alright, so let's look here. The idea is this is a base 10 logarithm. It's common logarithm. So if you were to exponentiate with a 10 on both sides, 10 to the log base 10 cancels and you get 3x. 10 to the log base 10 cancels again and you get 12. Well, that's a super easy question. You just get x equals 4. Some of the Algebra 2 kids always saw that question and said, well, can't I just cross off the logarithms? Yeah, because of the equation property, but what you're really doing is understanding that the exponentiation is what's canceling the logarithms. Oh my gosh, I don't like this question. We need to condense these logarithms together. So you have log base 12 of, if I were to multiply these together, I have 2x, you can use parentheses if you want, equals log base 12 of x plus 7. So if I exponentiate both sides with a 12, shoving a 12 base under, those are gone, and you get 2x. These are gone, and you get x plus 7. So we're going to solve, and you get x equals 7. So once again, I just got to go back and make sure when I plug in, I don't ever take the logarithm of something negative. If I do, I have to cross off that solution, and it is extraneous. Oh, yuck. All right. Ready to have fun with this? When you multiply these two binomials together into one new common logarithm, you end up with, yuck, I'm going to cheat and steal my answer from before, 320x squared plus 8x minus 4. So this is a common logarithm again. Blah. So exponentiating with that common base of 10 means these cancel, and we have a quadratic. This actually isn't going to be too bad. So when we bring everything to one side, subtract this over, I'm going to subtract that over, I'm going to add this over. Well, that was a really messy way to do it back up. Alright, there we go. So x squared minus x minus 2. So then we factor that x minus 2 times x plus 1. And I get x equals 2 and x equals negative 1. So again, I got to go back to my original setup and make sure if I were to plug in either of those that I don't end up taking the log of something negative. And I do think negative 1 is going to be a problem. For instance, right here. If I plug a negative 1 right there, it's going to be log of negative 16 plus 2, which is log of negative 14. That can't happen. So that's an extraneous solution. It'll give us non-real solutions. The only acceptable solution is x equals 2. Alright, more condensing. This time you have multiple logarithms to condense together. Good news is it's my favorite natural logarithm. So when I multiply these together, I get x squared plus 16x. And then when I multiply these together, I get natural log of 8x plus 48. So remember, we are technically exponentiating with the base. In this case, it's e, so that's how they cancel. And you get x squared plus 16x equals 8x plus 48. What do you know? You have another quadratic. All right, so x squared, subtract the 8x over. So plus 8x, subtract the 48 over. Oh boy, let's see, 12 and 4, will that work? So how about x plus 12 and x minus 4 for my factors? So solving those factors, okay, algebraically I get two solutions, but that doesn't mean they're going to work. Like for instance right here, I can't take the natural log of negative 12, so that one's gone. But it looks like 4 is going to work, so this is our only solution to that equation. Lovely, huh? Alright, so now we're going to be able to solve application questions without the use of a graphing calculator, at least not with the use of the graphing or table components. We're going to be able to solve algebraically for them. So this is our continual decay question, where your rate is decaying, so it's negative 0.00043t, and the initial amount is always that number that's in front. How long will it take for 50 grams to decay to 10 grams? So my final amount is 10. My initial amount is 50, and then it's e to the negative 0.00043 t power. So thinking about solving for my variable, my first step would be to divide by 50. So this is what, 0.2 equals e to the negative 0.00043 t power. And then I want to apply a logarithm to bring the exponent down. So since it's a base e, I'm going to be applying a natural log. So these cancel, but we have the natural log of 0.2, which looks like I didn't write that one down, sorry, equals negative 0.00043 times t power. And then my next algebra step would be just to simply divide by negative 0.00043. So this is disgusting. Definitely not something I would expect you to know off the top of your head, but turns out that t is approximately equal to 3742.88 years. And I know it's measured in years because it says right here t is measured in years. You do have to watch your labels. Sometimes on these questions they'll convert in the middle of the problem and you got to convert back, so just be careful about that. Alright, Richter scale. So those earthquake problems again. If the magnitude of an earthquake is 6.0, find the energy released. So this is the R. So if I place that into the formula, 6 or 6.0 is 0.67, and that's a common log of 0.37 times the energy. So solving this logarithmic equation, I'm first going to isolate the logarithm. Let's see if I wrote something down. I did finally. Alright, so 8.955 equals the common log of 0.37 times e. And then remember that's a common log base 10. So if you were to exponentiate with a 10, these cancel. And this is a huge number. So I'm not going to write it down right now, because 10 to the 8.955 still has to be divided by 0.37 to solve for e. So I think I already calculated this. And rather than writing down like this gigantic number and then dividing it by 0.37 to get an even larger gigantic number, I just wrote down the answer of 2, 4, 3, 7, 9, 3, 5, 1, 9, 2. Lovely. And I don't really know the label for the energy here. Oh, yes, I do. Kilowatt hours. Okay. Sounds like a lot. I'm not real sure. I'm not a seismologist or whatever they call those people. All right, so that is a little rundown of how to solve exponential and logarithmic equations. Yes, there's various different kinds, but the idea is for exponential equations, if you can find a common base, excellent, because then we can just do some algebra switching. If you can't find a common base, you need to apply a logarithm to bring the exponents down. If you have a logarithmic equation, no matter what it looks like, you're going to exponentiate both sides once you get to the point where you can. We're going to practice these a lot, and we're going to really focus on the application component of these because, you know, that's the real important part of this. Enjoy!